Hello and welcome to this Vivado quick take on the Design Analysis Report, an important new tool in the toolbox of time enclosure techniques. In this quick take, you will learn about a new Vivado tickle command called Report Design Analysis. It provides a key design information that is typically gathered by time enclosure experts. You will also learn where this command fits in the design flow, when it is used, and most importantly, you will learn about the different modes of analysis, timing, and complexity. Before we begin, we assume you are already familiar with the basic Vivado implementation flow. If you are not, we recommend you view these quick takes first. The Vivado Design Flows Overview, which covers synthesis and implementation, and the project and non-project modes of running Vivado, and the ultra-fast Vivado Design Methodology for time enclosure, which covers some best practices for successful design. Now let's introduce Report Design Analysis. It's intended to complement existing analysis by offering insight into the story behind the numbers you see in the timing reports, by highlighting certain characteristics that might point to time enclosure problems caused by failed timing paths and routing congestion. Report Design Analysis is currently tickle-only and is not run by default in projects, but can easily be incorporated into both scripting and project flows. There are two main modes of analysis, timing and complexity. While timing focuses on critical paths, complexity extracts general metrics from the design that can help pinpoint problematic parts of the design. Timing mode analysis is invoked with the dash timing switch and reports the important characteristics of critical timing paths, including key delay values from the timing reports, the path type, requirement, path delay, clock skew, and slack, also the number of logic levels, and a shorthand notation of the critical path structure. This helps you quickly visualize a critical path without actually seeing it in the GUI. The report includes physical obstacles in the path, the traversal of wide columns of block RAMs, DSPs, IOs, and for SSI devices crossing SLRs. Extra routing delay is incurred when crossing these columns. The highest fanout in the path is also reported. Other items include physical constraints, which may limit performance. For example, don't touch with mark debug will prevent logical and physical optimizations. P-blocks and fixed location assignments restrict placement, and finally fixed routes can restrict routing. The size of the region traversed by the path is given in terms of the absolute or RPM XY grid coordinates, and the number of clock regions crossed in the horizontal and vertical directions from start to endpoint. By default, the reported paths are the worst paths sorted by slack. However, there are other options. You can restrict output to setup paths only or hold paths. The dash max paths option controls the number of paths to report. The dash extend option will show the critical path side by side with its neighboring paths, the path to the critical path start point, and the path from the critical path endpoint. That lets you see how much slack could be borrowed from neighboring paths. Finally, you can choose specific paths by passing timing path objects with the dash of timing paths option. This is typically used with the get timing paths command, which is similar to report timing, except get timing paths returns timing path objects instead of a report. Let's take a look at timing mode analysis. Here we have a design that is finished implementation, and we see that it didn't meet timing. We can go to the timing path viewer and select the worst path and view the placement. And we can also generate a schematic and view the path logically. And we can also view the timing report, which breaks down the timing path to show every net and every cell delay. Sometimes it's challenging to put all this information together to understand the problem. Now we can run Report Design Analysis from the Tickle console. Looking at the report, we can see that our path crosses BRAMs 4 times and DSP columns twice. So floor planning to minimize crossings might be an option, but it's obvious that there are many levels of logic, 13 in fact, which might be too many levels. Now let's take a look at the extended path. We'll run Report Design Analysis, dash timing, dash extend. Now we see the critical path in the middle, but we also see the neighboring paths, both before and after the critical path. And we see that the neighboring paths meet timing, and there's plenty of positive slack that could be borrowed for the critical path. So perhaps we could apply retiming or modify the RTL to reduce the critical path levels at the expense of the neighboring paths. Recall that the command takes timing path objects to enable you to focus on specific paths. Let's see how that works. When we run with no options, we just get the worst path. What if we wanted to see the worst path from a DSP block? We can do report design analysis -timing -of timing paths, get timing paths -from all DSPs, and we see the worst path starting from a DSP block. Here's another example involving timing path objects. In the timing path viewer, when we select a timing path, let's see what actually gets selected. We'll run get selected objects. The first item is actually a timing path, followed by the cells in the timing path. To show that, let's run get property class get selected objects to see the class of each object. It shows that the first object is a timing path, followed by a list of cells, which are the cells in the path. We can actually select a path in the viewer, then run report design analysis on it. We just need report design analysis -timing -of timing paths, lindex get selected objects 0. The lindex or list index command grabs the first item at index 0, which is the timing path. We can go back to the timing path viewer and select a different timing path, then go back to the Tickle console, hit the up arrow and rerun the command, and we get the new path report. We can also define a toolbar button to perform this action under Tools, Customize Commands. Here we defined a command called RDA for Report Design Analysis, selected path, and the underlying command is the same Report Design Analysis command we just used. So we can select a path and press this button to get the path report. Now on to complexity mode analysis, which reports key complexity metrics of the design. The rent exponent is a metric based on Rent's rule, a commonly used measure of interconnect complexity in integrated circuits. A higher rent is often associated with reduced routability, but not always. The average fan-out of non-clocks also gives you an idea of the design complexity, higher fan-out indicating a more complex netlist. The LUT histogram shows the count of LUTs by size, LUT 1, LUT 2, and so on up to LUT 6. A design that heavily uses LUT 6 compared to other LUT sizes and experiences congestion may benefit from exploring synthesis strategies and other options that could result in more balanced LUT size distribution. In general, complexity metrics that measure in the high range don't always predict routing congestion or timing problems. But in the opposite direction, if your design encounters placement and routing trouble, complexity analysis often points to a problem spot that is most likely responsible. Therefore, the analysis is more of a confirmation. Here are the options that can be used with complexity to control the report output. The dash hierarchical switch reports the complexity metrics on a hierarchical basis, while the dash hierarchical depth switch specifies a number of hierarchical levels to include. By default, only the first level of hierarchy is included. The dash cells option can also be used to report complexity on specific non-primitive cells. Note that for very small cells, the metrics may be meaningless and the report will indicate that. Let's review an example. Here's a design that failed timing after routing, but the post-placement timing seemed like it was in good shape. If we check the log file, we can see that the router did report some areas of local congestion, where the routing resources were as high as 97% utilized. Viewing the placer congestion metrics shows some expected vertical routing congestion indicated by the heat map. If we zoom into a hotspot, we can see that the cells in this region are from the mem data instance in the design. If we run report design analysis -complexity -hierarchy, it shows that we have a relatively high rent exponent. The value of 0.83 for the top design is in the high range according to the scale, and the average fan-out of non-clocks is around 5.6. Both of these indicate a relatively high degree of complexity. If we look at MEM data itself, it also shows a high rent close to 0.7, indicating potential problems. The complexity analysis therefore confirms that MEM data seems to be a source of trouble. So, to summarize, Report Design Analysis is a new Vivado reporting command that provides unique insight into time enclosure problems. It often reveals some hidden characteristics of the critical paths and the design that are responsible for time enclosure problems. Use the command to complement existing analysis with its advanced analysis of timing paths and design complexity. For additional information, the best source is inside Vivado. Run Report Design Analysis-Help to get a list of options and their descriptions and explanations of all the report fields. Also see the following user guides: UG835, the Vivado Tickle Command Reference, UG904, the Vivado Implementation User Guide, and UG949, the Ultrafast Design Methodology Guide. Thank you for watching this Vivado Quick Take.